The last question of the final exam, question number 6, is on a DC motor. In this case, we have a separately excited DC motor here, and the circuit diagram is shown below. So separately excited mean that there's a different voltages for each of the field and the armature. So we're given the specifications for the voltage sources, and we're given the armature resistance and the field resistance, and we're given also conditions when the motor is fully loaded, so the steady state full load specifications. So what does that mean? When the motor is fully loaded, it produces a power output of 15 horsepower, and it'll have a rotational frequency of 1500 RPM. And what's really important for us is to know, or to notice, is that the rotational losses are negligible. So the P rotational is equal to 0. So then we are given the machine equations, the basic machine equations here. So there's 3 of them. So they'll be given on every exam, and we're also given some useful relationships as well. Now there's one more machine equation that you should memorize, and I'll just write it out here. P developed is equal to the armature voltage times the armature current. So you should definitely memorize that because it's very useful to know it. Okay, so memorize that. You can develop it from the other machine equations, but it's good to know it on its own. So then let's consider the first question. Part A says that the motor is operating at its rated capacity to help propel an electric vehicle up a hill. So when we say it's operating at its rated capacity, that means these specifications are in operation. Okay, so that's what we have to keep in mind. It's producing 15 horsepower at 1500 RPM. It's being applied to an electric vehicle and or a hybrid electric vehicle, and that's really interesting. Not for part A, for part B, we're going to see something interesting. So under full load conditions, so that's the same thing as saying at rated capacity, we're supposed to find the output torque, the armature voltage, the field power loss, armature power loss, and efficiency. So let's start doing those one by one, and let's find T out. So that's the output torque. So what is it that we know? We know that the output torque is equal to the developed torque minus the rotational torque, like the losses of the torque from rotational losses. So basically the friction losses at the bearings and the windage, which is the air resistance as the motor is turning internally. So in this case, we said that the rotational losses for this machine are negligible, so that means that this term is going to disappear. The rotational losses are negligible, so T rotational is 0. So then T out is equal to T developed. Okay, the torque output is equal to the torque developed. We can also say, as an aside, that P out is equal to P developed. Normally we subtract the power from the rotational losses, but in this case this is also going to be true. So now let's continue. So how are we going to calculate the torque output? We have a machine equation, and we're going to use this one here. Power is equal to torque times the rotational speed. So now look at that machine equation. Power is equal to torque times rotational speed. Now why did I write it in terms of power developed is equal to the torque developed times the rotational speed? Well, this machine equation applies in all cases with the specific interpretations. We can say P out is equal to T out omega m, or we can say P developed is equal to T developed omega m, Or we can say P rotational is equal to T rotational times omega m. So those are all the different interpretations that we can have for that particular machine equation. And that's why I used the one that was useful for me. So what we know is that we know the power developed, and that's 15 horsepower. Now we have to convert that into watts, so we're going to use our relationship for horsepower and convert it into watts. So then 15 horsepower times 746 watts per horsepower works out to 11,190 watts. So that is the power developed. So then what else do we need to be able to calculate the torque? We need the rotational speed. And we have been given that the motor operates at 1500 RPM, and then we have to convert that into radian frequency. So then how we do that, we can use this relationship. If we don't know it, it's very easy to come up with it. So we just multiply by 1500 by that scaling factor, and then we get 157.08 radians per second. So now we know all the information we need to calculate Tdev, okay? Because we know Pdev and we know the rotational speed. So down here, we're solving for the developed torque. That's the output torque. And so it's just 11,190 watts divided by 157.08 radians per second, and that gives us 71.24 Newton meters. And that is our answer. And in fact, let's just make it explicit. This is the torque out. And that's because torque out is equal to torque developed when the rotational losses are zero, as we said at the beginning of this. So this is why that's true. Okay, so now let us continue on the next step. So we are supposed to find EA. So where is EA? EA is here. It is the armature voltage. And what the armature voltage is, it's the back EMF that's developed when the rotor is turning, and then the rotor is turning inside an electromagnetic field which is created by the field inductance, and current is induced, which in turn is represented by this armature voltage. Okay, so the faster the shaft turns, the larger this EA is going to be. It's an induced voltage. How are we going to solve this? Well, if we consider that we want to find EA, and look what we know. We know VT is equal to 240 volts, and if we happen to know what the voltage across the resistor is going to be, then we can use KVL to find EA. And what's more, lucky for us, we know the armature resistance and we know the current flowing through that resistor, so we can easily calculate the voltage. Okay, so the voltage is simply the current times the resistance, and when we plug in the values, we get a voltage across that resistor, across the VRA resistor, of 9.998 volts. Okay, so that's our first result for solving for EA. So then we can do KVL going clockwise around the armature circuit, and so then for the terminal voltage we get minus 240 volts. We calculated the voltage across the armature resistance at 9.998 volts, and then we're going to solve for EA. And so then we get a value of 230 volts for EA. So that is our second result for part A. So next, we're going to calculate the field power loss. So then the field power loss. So what does that mean? So this is the field circuit. So the field power loss is the losses, the electrical losses in this circuit, and the only place that electrical losses can occur is through this resistor. So we need to find what's the power dissipated in this resistor. So then, what do we know? We know the resistor value, okay, which is 150 ohms, and we know the voltage applied to it. We also know that in steady state, there is 0 voltage across this inductor, okay? So that inductor voltage is going to be 0 volts. So all of the voltage, all of the 120 volts is going to be dropped across that resistor. So then we can use our formula. So this is just straight electric circuits. So the voltage squared divided by the resistance is the power. And then we plug in our values. So we have 120 volts, which was the field voltage, divided by 150 ohms, gives us 96 watts. So that is PF. Okay, so we've solved for PF. Now, what's the next thing that we're supposed to solve for? The armature voltage. So that's a result. So I'll just put a little box around it. So we're gonna solve for the armature power loss, PA. So this is a little bit confusing because, you know, is PA the power in the armature or what? Okay, so actually PA refers to the power dissipated in the armature resistance. So then how are we going to solve for this? Well, what do we know that's useful to us? We know the armature resistance, and we know the current flowing through the armature. So we can just use I squared R to solve for PA. And that's what we're going to do. So the armature current squared multiplied by the armature resistance, plug in the numbers, and we get the armature power loss of 486.38 watts. So that is fourth result for part A. And now the last thing we have to do for part A is to find the efficiency. So how are we going to do that? Well, our efficiency formula is the power out divided by the power in times 100%. And this is going to be, well, it's going to be lower than 100%. We can never get above 100% efficiency. So then, we know that the power out is 11,190 watts. And we solved that in part A earlier, okay? So that is just simply converting that horsepower. So then we need to know what is the power in. We need to solve for the power in. So what's the power in for an electric motor? Well, it's going to be the power of the field, and it's going to be the power in the armature. So that's basically going to be the voltage times the current. So what do we know? We know that we've already calculated the power in the field as 96 watts, and the power in the armature is going to be the terminal voltage times the armature current. So that's the total power going into the armature. We know that the voltage is 240 volts and the current is 48.65 amps. And then we get total result of 11,676 watts. So now we know both the power out and the power in, and our next step is to add them up. So that's power in, and then we are going to apply it to our formula. So P out divided by P in times 100% is the formula for efficiency, We plug in our numbers that we found for P out and P in, and we get an efficiency of 95.06%. So that is our final result for part A. So then the next part is part B, and we're supposed to find the power in the 240 volt source with the condition that now the vehicle is descending rapidly on the other side of the hill, and the physical torque reverses on the motor shaft. So this reverses bit is really important. The new torque is minus 30 Newton meters, and we have a note highlighting that it's negative now. And then now we're supposed to determine the power in the 240 volt source and indicate whether the source is absorbing or delivering power. So now this is very interesting what's happening. The vehicle is going downhill, and what's actually happening is that now the torque has reversed on the motor shaft. So what that means is that the motor shaft is actually slowing down or trying to slow down the car. And what's happening is that the energy is going to be going back into the battery. So I'm just forecasting a little bit about what our final result is going to be. And this is actually an application of regenerative braking, if you've heard of that. So how are we going to solve for this? We know the power in the 240 volt source is going to be minus VT times IA. Now why do we have the minus sign in here? Well, look at the reference direction that is shown in the figure. So we have the IA current flowing in this direction, right? It's flowing into the negative and out the positive. So we use the negative sign, okay, to denote that power relationship as drawn. Okay, so then let us continue. So now, since we've got a new situation, we're going to have to calculate some new things. So we have a new torque value, so that now the EA, now the EA is going to be different, right? Because we don't know what the new speed is. We have a different torque, so a different EA is going to be produced. And if a different EA is going to be produced, we're going to have a different IA. Okay, so we need to find the new IA for question B, for the circumstances that's described in question B, part B. So then, to find IA, I'm going to use the machine equation. The torque developed is equal to K phi IA, where K phi is the machine constant. So then what we're going to do is we're going to go back to our original part A to get values to solve for K phi. So we already know minus 30 Newton meters, and we need to find K phi. So we're going to use the same equation. T developed is equal to K phi times IA, but we're going to use the values from part A. So we're going to solve for K phi. So it's torque developed divided by the armature current, and we have values for that from part A. So 71.24 Newton meters for the torque developed and 48.65 amps. Okay, so then we get a machine constant of 1.464. So then we can plug that back into the formula, and knowing K phi and T developed as being minus 30, then we can solve for the new armature current. So that's what we're going to do. So IA is going to be the new torque developed times K phi. K phi stays the same in both cases, okay, because the reason why K phi stays the same is we haven't done anything to change the field circuit, okay, so it still behaves exactly the same. It delivers the same flux phi. Okay, so we plug in our numbers, minus 30 Newton meters and 1.464, and we get an armature current of minus 20.488 amps. So that's interesting. So we have a negative armature current. Okay, so if we take a look at the armature current here, that was positive. That was positive 48.65 amps. And now we've got minus 20.488 amps. So what that means is actually our IA current is flowing in this direction. So let's say new IA. So what does this mean? Well, I mean, think about it in terms of electric circuits. The only way the current can flow from right to left now is that the EA has to be greater than VT. That's quite interesting. So there's being some energy developed on the actual armature side from the rotor. Okay, so then how are we going to use this information? Well, we're going to calculate our power. So going back to the original equation that we had up here, we're going to reproduce it down below. Okay, and then plug in our numbers. So we have the minus sign that we add here, so that stays the same. We put in the value for VT, which is 240 volts, and then we multiply it by the current value that we just found, minus 20.488 amps. And then we get a value of 4,917 watts. Okay, so that's positive, so that means it's absorbing. Okay, and then what the implication is that the VT source is being charged like a battery, and this is the application with regenerative braking, which is one of the really nice things about electric vehicles. So if you're going downhill, you can use the motor to slow you down, and when you're using the motor to slow you down, it's operating like a generator, and it generates electricity and puts it into the battery. And I understand the typical range that regenerative braking adds to an electric vehicle is something like 10 or 15%. Okay, so it's not a huge difference, but a difference nonetheless. Okay, so that's how to solve question 6.